Yeah, hello everyone. Today we are building the shortest path generator together in C-Notes. I built one already with Python maybe a half a year ago. So I tried to do this also in C-Notes and it worked out very good. The performance is pretty nice. So I thought we can build a simple version together. And at the end, I will show you the advanced version and show you this setup here where you can build a tree. And I explain some of the settings of the advanced one. But before we start, I want to give you some updates. I built an update for the Plexus effect. There is now, you find this in Gumroad, also a Plexus generator that can build polygons, as you see here in this example. And I also updated the Spline Relax solver. Thanks at this point to the guys from Maxon. They gave me good insights and some tips how to optimize the whole setup. So now it's much easier and also the performance is also a bit better. Okay, I think now we can start. So what we need first is a surface. Best is kind of a triangulated surface. So let's build a simple one. Let's build a plane. And then best is to use the poly reduction to make some triangles. I think we need some more. I think something like this is okay for a start. And what we need next is we need selections, actually two selections, one selection for the start points and one selection for the end point. So we put the poly reduction under a connect object. Then we are using a point selection. This one is our start. Another one. This one is our end. Next, we like to have fields to decide where our start and end points are. So let's use a spherical field, call this start, maybe the inner offset, kill it, and then place it maybe here, something like this. Then also one for the end, around here, it's okay. And then place the end field inside the endpoint selection. So let's start with the node setup. Because we are building splines, we are using a spline capsule. So search for group. And there is the spline primitive group. And now let's open it. Maybe rearrange the windows here, so we have some more space for the nodes. So first what we like is we need our connect object as a child here, so put it under the spline primitive group. Then add a child node, child operator, put the operation here as a new input and also the children as a new input. Then go to edit resources and switch the children to object here, the scene port mode to object. And now you can see here is our child and here is the geometry of our child. So what we need first is our two selections. So we can use a selection to index here, selection to indexes. Feed in the geometry. We need it twice. So this one is our start and this is our end. Then here in the selection string, place the start here and in the end also the end selection here. And now we have two arrays with the indices here of the start points and the end points. And if we like to check if everything works, we can use a get element to take the first index of the start points and the first index of the end point. And then we can build an array. So what we need is the positions from the geometry. So we use a property geometry property get. So, and what we need is the 3D points. So then let's build an array with vectors. We just need 2 points. And then we need 2 other get elements. To get the actual point position. So feed this in here, and then this one inside here. So, and now with a assembly spline, we can show here our line, and maybe let's make here an instance of the mesh so we see the mesh. So maybe let's make it X-ray, zoom in, and maybe the line, give it also a color, custom, maybe bright red. So, and now you can see this is the first start point and this is the first end point. And when you move this around, you can see it jumps around. So this part works. So to build the actual algorithm of the shortest path, I want to explain it. So let's make a doodle. So let's zoom in. So if you say, okay, this is the start point, and the start point here, you can see it has like 1, 2, 3, 4, 5, 6 neighbors. And here's the endpoint. So we have to, we want to know the neighbors. So all those. And then we measure the distance from the endpoint to every neighbor. Like this. And then we have to compare all those distances and decide which one is the shortest. So for this example, it's this point. So then we are building an array with the points starting from the start point. Then the next point is this one. And then we have to update the start point. So the new start point is this one. We do the same procedure, and then it goes like this. And it goes to the endpoint. And so that's the way we are building those shortest paths. And at the end, we are doing this for all the start points, but first we are starting with just one start point. Okay, because we like to update always our start point, we are building the next part inside of a loop. So first let's delete this stuff here. And then we are using a loop. It's called loop carried value. So, and what we like to update here is our start point. So the start point is here is an integer, so you can name it maybe new start point or new start index. And then what we need inside the loop is also our geometry. Then our endpoint, call it end index. Then our start point is the first new start index here. And then we need also an array where to store all those points to build at the end a spline with the assembly spline. So we use a build node with vectors inside. Then because the first point we already have here, this is the start point. So we use an get element, feed in the start point index here, and then our points, and feed this in here. So the first point here in our path array, maybe let's call it path array. Yeah, there's the first point is already in there. So, and now we can feed in the array also inside of the loop. And now we have to decide how many iterations the loop needs. So if we have one iteration, it goes just to this point. If you have two iterations, it goes to this point, and so on. So we can decide this with a range node. So, and here we can build iteration. So from start to end, we can propagate the end outside of our capsule here. So call it iterations. So we can say here on the capsule how much iterations it has. So we start with just one iteration. Then we plug in here the curly bracket to the loop here. So now the loop as often as our iterations here. And last, of course, we also need our geometry. Now when we jump inside of the loop, now the first thing what we like to have is the our neighbors here, our neighbor indices of the start point. So there is a node called geometry neighbors. So here we see we need the geometry, and then the index is our start point. And now here we have an array with the indices of all our neighbors. So these are those points here. So next we need all the distances. So here the white lines here. So we have to measure the distance from all the neighbors to the endpoint here, to the end index. So let's use first an iterate collection to iterate over all the neighbors. So now here we have all the neighbor indices. So then let's use a get element again. Then feed in our array here. These are our points. Call it points array, and feed in the index elements here into the index, and call this maybe get neighbors. Oops. And then of course our endpoint. So also inside here. Then this is the position of our endpoint, and these are the positions of all our neighbors. And now we are measuring the distance between those two vectors. Distance. Now we have here the distance, and now we have to decide which distance is the shortest, and also the corresponding point to this the shortest distance. So we have to find this point here. So we use a loop for this. Then remove here the first input and add two new ones. So they're both vectors at the moment. So the first is an integer, so our index, and the second one is a float, so our distance, shortest distance. And let's call this one distance, shortest distance, and shortest distance, and test index. Then we feed in the current distance here, call it current distance, and also the current index. So, not the element, this one. Call it current index. Maybe switch those. And now the loop has to run for every neighbor point. So for every neighbor point, we need one loop. So we can port here again the curly bracket here to the other curly bracket. So now for every neighbor, there is a loop. I accidentally deleted the shortest distance here. So add it again, add an input, call it shortest distance. Shortest distance. Here we go. And now before we dive into the loop, the shortest distance, the initial value has to be a high value. So maybe let's make 999. So this is a huge value. Then let's jump inside of the loop. So now we have to compare the shortest distance that is now here. There's 999. That's a huge value with the current distance. So, and check if it is smaller, the current distance is smaller than the shortest distance. So use a compare. So then feed in the shortest distance and the current distance and ask, is it less? So is the shortest distance, the other way around, is the current distance less than the shortest distance? And if this is true, we get here true. And now we need two if statements. Use here a if, use it twice, feed in this to the conditions, and now here we can decide what happens when this is true and when it is false. So first switch this here to a float value. So now if it is true, the current distance will be our new shortest distance. And if it is not true, the distance shortest distance remain the same. So put this here into the false. The same we have to do with the index. So here, if it is, if it is true, the current index will be our new shortest index. And if it is false, the index remains the same. So that's it for this loop. So let's jump back. And now here we have the index. So the closest index here to our endpoint. So this index here. And what we like to do now is to add this point, this vector here, this position to our path array here. So let me use an append elements for this. So we like to append to our path array, and the value here, the position, we have to extract here from our points array. So use a get element, feed in all our points here, then the index is our shortest index, and then append this to our final path array here. Then the final path array can go outside of this loop. And now, because we are finished here with the first iteration, we like to update our new start position. So this was our first start position. Now we like to search in the next iteration from this point. So our shortest index here updates here the new start index. So, and if now everything is correct, we can now feed in here our array. So this is here our path array, or maybe call it final path array. Feed this in here to our assembly spline. Then hide the doodle here, and now we can see it builds here for the first iteration connection from here to here. And now with let's zoom out a bit, make it a little bit bigger. And now here with the iterations, you can see it goes here to the endpoint. This one here is our endpoint. And we see we have two problems. First is we have a Bezier spline here. So here in the assembly spline, the spline type is Bezier, but that's okay for later. So, but we can also switch it here inside of the spline primitive group here under subdivision. You can use linear and none. So, and there's also another problem. So, because when we are reaching the endpoint, the loop goes further, so we have to stop here at the endpoint. So we don't want to iterate more than here to our endpoint. To achieve this, let's jump. Maybe first switch it here back to B-spline with some points here, so we can see it when we zoom in. You can see here when we check the iterations, so it goes here to the endpoint, and when we go further, it jumps back and forth here. So actually we want to stop it here. So let's jump inside here our loop again. And here we have to compare the current start index with our endpoint. So compare. So we have to check if here our new start point is not equal to the endpoint. So if they are not the same, we can here use the count parameter. So we can say, okay, as long as they are not the same, we can add new points, and you already see it jumps back here. So let's say this back to linear. And finally, we need an if statement. So here we have to decide if they are not the same. So if this is true, so this is true, the new start index is updated, and if this is false, so if it reaches the end, the new start index remains the same. So that's it. So now there will be, as it doesn't matter how many iterations we have here, it stops if the start point reaches the end point here. Now we have a path for the first point here in our start point selection, and now we like to have this for every start point. So that's not too complicated. So let's go back here, and then here are all our start points. So we don't just get the first one here. We like to iterate. Maybe put this here a bit down. And now here start point, we use a iterate collection. So we iterate over, oops, not the index iterator, use a iterate collection. And now we iterate over all our start points, and then all our elements here will go here first inside of the get element here, and also inside of the new start points. And now we have to save for every start point iteration. There has also be a whole range iteration. So then now it disappears. So that's because now here we get more than just one array. So we have now for every start point, we have our own array, and the assembly spline needs just one array here to show it here inside of the spline primitive group. So we have to first assemble an final array. So let's build our final array here. Type is vector. Remove all of those. Then use an append element. And then here our final, we need all the points from every array here. So every array is one path. So use an other iterate collection for this. So iterate over every array here and feed those elements here inside our final array. Maybe call this and this will go inside of the assembly spline. And now we can see here are the lines, but the problem is if one path is finished, so the spline jumps back to the second one. So we have those lines. So we also have to design here the segments. So that's pretty easy. So we need another build. So we need an array with just integers. So remove all of those, and then also an append element to append here to our, call it segment array. And the value is actually is the count. So every path has a different amount of points inside. So these are actually the values for our segments. So feed this into the segments. So now it knows how much point every segment has. And we can see here we have our final paths here. So now we can take the start here, for example, make it bigger, move it around. Maybe let me show this a bit bigger here. And here also the endpoint. Maybe hide this. And that's it. So this one here will be the file that you can download on Gumroad. You have here 3 setups. Here is the simple one. That's the one that we built together. So let's zoom in. Here you can see with one endpoint here. You can move this around, and with the start point. And then there is an advanced setup here. This one has some more parameters here. The mode here I will explain at the end. What does it mean? Also have search iterations. This is the same in the simple setup. And here you can switch between just one endpoint. So it uses just one endpoint, or you can use all the endpoints. So I have here for the endpoint selection here, I have a linear field. So here are all those points on this side are endpoints. So all the start points searching the shortest path to all the endpoints here. And here the last setup is the tree setup. So let's hide those two. And here in the tree setup, let me explain this. Here you can find our shortest path, the advanced setup. Then here inside our connect object, there is another capsule. Let me show this capsule here builds this volume mesh structure to build the tree setup. You can dive in if you like here it is and have a look how it works, but I don't want to go into detail here. So now let me show you how to paint trees. We have here a spline, so let's delete all the points, select all, delete all the points. When you deactivate and activate here the connect object, now it is empty. So now we can go here into the tree spline, select the sketch tool, for example, and now we can start to paint trees. And you will see already now here there are some issues, and that is why I built also an accurate mode. So when you switch on the accurate mode, those issues will disappear. And now I like to explain how the accurate mode works. So I have here an example scene. And now you see the mode here is on the fast mode, not on the accurate mode. And the problem is when we here raise the iterations, it here walks through. And now we can see here there is a problem. When we zoom in, it jumps back and forth. And that is because here our endpoint here is here. And when we jump from this point to this point, and this point now searches over all the neighbors, and it sees that the next closest point is this one, so it don't goes in this direction, it jumps back. So that's the problem here, but so that's why I built an accurate mode. It is a bit slower, but with this mode, it is not allowed to jump back. So now it works. And then some last tips for the tree setup. If you like to have kind of different tree variations, you can work with different settings here. First off, the random effector here that randomizes our our mesh here. So when we activate it here, then you can see we have different trees. And with the smoothing here, when you up the iterations, the tree gets smoother. And the last setting that is also valuable when you go back here to one iteration, is in the shortest path settings under subdivision. Here you can, now we have linear, so we can say there are no intermediate points, so it also gets kind of smoother. And when we go back here to maybe uniform and up the intermediate points here, you can see it gets more accurate and it looks more spiky here. So yeah, that's kind of the three settings where you can play around. So first here the type and the intermediate points, then here with the random effector, and then of course here with the smoothing deformer, so up the smoothing here. Yeah, that's a way where how you can create different trees. So yeah, that's it. I hope it wasn't too complicated. I hope you can follow it along. So, and of course, if you have questions, let me know in the comments. And the scene file, of course, you will find in the description. There is a link to Gumroad where you can download it. Yeah, I hope you like it, and I wish you a nice day. Bye-bye.